says which of the following represent the correct order of decreasing freezing point. So here we have total 4 compounds: KNO3, CaCl2, glucose and copper sulfate. So we have KNO3, then calcium chloride, glucose and copper sulfate. So their concentration is given in molarity and we have to arrange them as decreasing order of freezing point. So what is the relationship of freezing point with concentration and the I factor, that we have to know. So del TF is equal to I into KF into molality. Okay, but here molarity is given, that is capital M, but it does not matter anything because we have to take the relative order. Okay, so because for all of this we are taking the value of I into M, and in place of small m if we put capital M here, there will be no problem. Okay, so del TF is basically TF naught minus TF, because we know there is depression of freezing point, so TF naught, it will be having higher value compared to TF. So this difference is actually del TF, and this is equal to I KF into concentration. Now here TF naught, that is fixed because all are aqueous solution. So that means the freezing point of water, that is fixed, which is 0 degrees centigrade. Now when we are adding different types of solute, that is KNO3, CaCl2, glucose or copper sulfate, depending on the concentration of the solute, the TF will vary. Okay, so here I will be different for all these species, because when KNO3 is dissociated, there is K plus, NO3 minus. When calcium chloride is dissociated, Ca2 plus, 2 chloride. When glucose, there is no dissociation because it is non-electrolyte. When copper sulfate dissociated, copper 2 plus, sulfate ion. So I value for KNO3, it will be 2 because only 2 particles. I value for CaCl2 3. Here I value is 1 and here I value is 2. Okay, now KF is also fixed because KF, that is dependent on the value on the nature of solvent, and solvent is common for all of these 4 species. So KF will be same. So here TF is constant, KF is constant, but TF, that is the value of TF, that is dependent on the value of I and M. Now I we have already calculated here, and M is given in the question. Okay, so here higher the value of I into M, lesser will be the value of TF. So we can write higher is the value of I into M, lesser will be TF, which is clear from this equation, because right hand side I into M, KF is fixed, I and M may vary, and in the left hand side TF naught is constant, but TF naught, it can vary. So that means as there is negative sign before TF, so higher is the value of I into M, higher will be TF. Now in case of KNO3, I into M, in case of KNO3, it will be I is 2 and 0.05. So what will be the value? It will be 0.1. Then I into M for calcium chloride. This is 3 into 0.04, 0.12. Next is glucose. Now for glucose, it is simply 1 into 0.14. So it will be 0.14, and the last one is copper sulfate. So for copper sulfate, this will be 2 into 0.075. So again I am saying here in place of molality we are putting molarity, but that is not a problem because we are taking we want to see what is the relative order of the value of I and M for all these species. So if we have molality, then also we will have the same order for all these 4 values of I into M. So it doesn't matter whether it is molarity or molality here. Okay, so it will be 0.15. Now if we arrange all these 4 species according to the value of I into M, maximum I into M value, that is for copper sulfate, that means TF value that will be minimum for copper sulfate. Okay, now if you look at the options, only in the first option copper sulfate is at last, that means it is have minimum TF, and we have to find the correct order of decreasing freezing point. That means this is having maximum TF, that is the first species, and the last species that will have minimum TF. And from these values we can see that 0.1, that is IM value is minimum for KNO3, that means TF will be very low. The value of TF will be high. Okay, so the decreasing correct order of decreasing freezing point, it will be this one, that is option A. Okay, so here we are considering the numerical value of TF. Okay, so as this value is very low, that means here the depression that will not be, that is if we consider the total del TF as it is fixed, so as this value is maximum here, because the right hand side I into M is low, so TF will be maximum, that means this difference that will be low. Okay, the next problem, a 0.001 molar solution of PTNH3 whole 4 Cl4. So this is a complex molecule in water, had a freezing point depression 0.0054 degrees centigrade. So here del TF value is given. Okay, now Kf value for water is solvent here, that is given 1.8. So we have to find out the correct formula for the above compound, and we have to assume that its dissociation is complete. Okay, now this is a coordination complex, fine. So there will be a coordination sphere. So inside the coordination sphere, whatever moiety is there, there will be no dissociation, only the species which is present outside. Suppose if it is 2 plus, I am just writing arbitrarily, and outside there is 2 chloride, that means 2 Cl minus. So when it will dissociate, you will get cation, which is basically the species inside the coordination sphere, 1 cation and 2 anion. That means here I factor will be 3. So if we can know what is the value of I, then we can easily find out what will be its formula. And see, here ammonia is neutral ligand and chloride is ionic ligand. So obviously only chloride can remain outside, because the bond between the coordination, this cationic moiety inside the coordination sphere and the ion which is present outside, this interaction is ionic. But neutral ligand cannot reside outside the coordination sphere. Neutral ligand ammonia, it will always be inside the coordination sphere. Okay, so for ammonia, that will be inside the coordination sphere. So you can also see, if you look at the options, in all the options, all the 4 ammonia molecules all are inside the coordination sphere. Now we have to choose that in which case, that is if you consider this complex, it will dissociate as PTNH3 whole 4 Cl3 and plus and Cl minus. So here I value is basically 2. For the second one, you will get the cation, which is the moiety inside the coordination sphere, and 2 Cl minus. That means I value is 3. Here I value is 4. Here I value is, that is not possible because it is simply 1. because it is not dissociating. Outside the coordination sphere there is no ionic bond. So if we can know the I value, we can easily understand what can be the formula. Okay. Now here for determination of I value, we need the molality and we need the Kf value and freezing point depression. So these three things are given, that is del Tf value, Kf value and molality. So we can easily find out what will be the value of I. So here Tf, in place of Tf we have written 0.0054, I is unknown, Kf is 1.8, molality 0.001. So here I value is 3. That means which option will be correct? It will be the option B, because when it will dissociate we will get Pt NH3 whole 4 Cl2. So here it is having coordinations number 4 plus 2, that is 6 coordination number, and outside we have Cl2. So it will dissociate as plus and 2 Cl minus. Okay, that means I value is 3. But if you consider other options, that is A, C or D, here I value is not 3. For the first case I value is 2, here I value is 4, and here as it will not dissociate it is simply 1. Okay, so correct option will be option B. I and the extent of association and dissociation. Now we know what is I, that is Van der factor, and how to include Van der factor in the colligative properties expression. But if there is association or dissociation, in that case, if suppose the association and dissociation it is not complete, so that is why we are saying extent of association or dissociation. So suppose we have KCl molecule and we say that I is 2. Why we say that? Because when we are saying that I is equal to 2, that means we are assuming that there is complete dissociation of K plus and Cl minus. Okay, but it may not be the case always. Suppose there are total 10 moles of KCl and only 9 moles are dissociating. Though KCl is very good electrolyte, it will always dissociate 100%, but it is not required that all the electrolytes will dissociate always 100%. So suppose there is out of 10 moles only 5 moles are dissociating. That means 5 moles, for 5 moles I value is 2, but for the rest of the 5 moles which are in non-dissociated form, there will be I value 1. So that is why the extent of association or dissociation, these two we must know. That is what is the percentage of dissociation or degree of dissociation or association. Okay, so there is a relationship between this Van der factor I value and the extent of association or dissociation, that is the degree of dissociation and association, which is denoted by alpha. Okay, so what is the relationship between I and alpha? That formula we will establish here. So here n is the number of particles dissociated and alpha is the degree of dissociation or association. So here we have taken A and it is dissociated to n number of particles. Okay, so P is product basically. So initially we have 1 mole. Suppose we have 1 mole. You can also take X mole, it doesn't matter. And at equilibrium it will be 1 minus alpha, because out of 1 mole only alpha percentage is dissociated. So undissociated amount is 1 minus alpha. So if you are considering it X mole, it will be X minus alpha. Okay, and from 1 mole of A there is production of n moles of P. That means if it is alpha is the degree of dissociation, for each alpha there will be n alpha amount of P. So that is why at equilibrium, when alpha amount is dissociated, rest of the amount of starting material A is 1 minus alpha. So obviously the number of particles for P will be n alpha. So total number of moles at equilibrium will be, simply add these two values, 1 minus alpha plus n alpha. Now total number of particles, this is actually I. So I will be equal to this value. Okay, so initially there is 1 and now the total number of particles, that is 1 minus alpha plus n alpha. So finally the relation that we are getting between alpha and I is this relation. So this relation we can use when there is dissociation. So this particular formula, this is for dissociation, but we will also see what is the relation between I and alpha when there is association. So the next example is for association. Here, starting from Na, now as it is association, number of particles will decrease after association, so that is why it is An. So you can take simply the example of two molecules of CH3COOH, and after association it will be converted to CH3COOH whole N. Okay. Now here, as we are discussing extent of association, that means all acetic acid molecules will not be converted to this associated form. Some will remain as normal acetic acid molecule. So that is why the question of degree of association arises. Okay. So initial moles of Na is 1 and for An it is 0. Then at equilibrium again it is 1 minus alpha, because we have considered alpha is the degree of this association. So for each Na, that is when Na is converted to An, that means there will be alpha by N amount of An. Okay, because it is now decreased. In the previous case what we have done, we have multiplied the N with alpha, but now it will be alpha by N. So it is the decreased value. So total number of moles will be, simply add these two, 1 minus alpha plus alpha by N, and this is equal to I. So the relationship now is I minus 1 by 1 by N minus 1. It is actually, if you can remember this, it is very easy to remember the second one, it is because only difference is in place of N, now we have written 1 minus N, 1 by N. That is the only difference, otherwise both the formulas are same. Okay, so if I value is known, we can find out the degree of association or dissociation, that is alpha, and if alpha is known, that is the degree of dissociation or association is known, then also we can find out I. Okay, because this relationship is between alpha and I. Okay, so now we have a problem which is related to this type of extent of dissociation. So if we solve this problem by applying these formulas that we have just calculated, then the idea will be more clear. So here the solute is AB2. Solute is AB2, and here 10% dissociated. That means alpha will be 1 by N, 10. Water is solvent, and AB2 after dissociation it will be converted to the cation A2 plus and B minus. Boiling point of 10 molar aqueous solution, that means molality is also given. So boiling point, so there is fill in the blank. So we have to basically find out what is the boiling point and rounding of the value to nearest integer. The Kb value for water is given, and boiling point of water it is 100 degrees centigrade. Even if it is not given, it is fine. Okay, so AB2 it will be dissociated as, there will be 1 cation and 2 anion, 2 B minus, right? So here N value is 3, because after dissociation we are getting total number of moles A2 plus and 2B minus. Okay, so N is 3 and alpha is 1 by 10. You can also write it as 0.1. Okay, now remember the relationship between alpha and I. Alpha is equal to I minus 1 divided by N minus 1. So we will put the values of alpha. I is unknown, 3 minus 1. So from this equation you will find that alpha I is 1 plus 0.2, 1.2. So see here I value we are getting 1.2. So this is actually not a whole number. Normally if the extent of dissociation is complete, suppose 100% dissociation, here it is 10%, but suppose it is 100%. In that case I value it will be same as that of N value, that is total number of particles, because there is no AB2. But when we are saying that 10% dissociated, that means only 1/10 amount is dissociated. That means 1/10 will be in this form, cation and anion, but rest of the 90% that will remain in undissociated form. So that is why now the I value is not whole number, it is a fraction. Okay, so now we know what is the value of I. Next, from this relation, del TB, which is equal to I into Kb into molality. So now put all the values. This is 1.2, Kb value is given 0.5 and molality given 10. So this will be equal to 6. But here del TB is not asked. Here boiling point is asked. That is, after increasing boiling point, what is the final value, that we have to find out. So del TB is basically TB minus TB naught. Now del TB we have calculated 6. TB is unknown and TB naught is 100. So TB will be equal to 106 degrees centigrade. So here in the fill in the blank. So this is round off to nearest integer. This is a integer value. Okay. So in this way we can apply this formula. Similarly, if there is association, mostly you will find the questions related to dissociation, but if it is association, simply in place of n you have to put 1 by n. That is the difference. Another problem, now this is also related to dissociation or association, though if we read the question at a first glance it doesn't seem so, but actually this is also related to dissociation. So freezing point of NaHSO4, its molality is 0.08 and freezing point is given. So percentage of HSO4 minus that transfers a proton to water to form ion, that we have to find out. Now what is the meaning of this line? That is important, because here if it is directly asking that what is the percent of dissociation of NaHSO4. So NaHSO4, it will be dissociated to Na plus and sulfate ion and H plus. Okay, so if it is directly asking that what is the percentage of dissociation of NaHSO4, this is the question is very simple, but here it is asking the percentage of HSO4 that transfers a proton to water. Now HSO4, it transfer proton to water means what? In presence of water it can supply H plus. That means now there will be H plus plus H2O, which will be hydronium ion and sulfate ion. So that means basically we have to find out the percentage of HSO4 that is dissociating to H plus and sulfate. So it is asking actually the percentage of dissociation of HSO4, but it is asking in indirect way. Okay, so you have to read the question very carefully, that what it, once you understood what is actually the question, in the question it is asking, then it will not be very difficult. Fine. So first we will write what is the dissociation of NaHSO4, and you can also take here water. If you omit water, then also it is fine. So it will be Na plus. Suppose you have not written H2O, in that case you will write H plus, but as we have written H2O, so we will write H3O plus and sulfate. So this will be the dissociation products. Now when T is equal to 0, then the amount of NaHSO4, suppose there is only 1 mole, and water as it is present in excess, we will not consider anything for it, and Na plus, H3O plus, SO4 all are 0. Now when T is equilibrium when it is reached, now alpha is the degree of dissociation, alpha is degree of dissociation, so it will be 1 minus alpha, and for each mole of NaHSO4 there is 1 mole of each, so it will be alpha, alpha, alpha. Okay, so now the total number of particles, what is the value? It will be 1 minus alpha plus 3 alpha actually. So it will be 1 plus 2 alpha. Okay, so now we know what is the value of total number of particles which is present at equilibrium. Okay, so now the formula, that is del Tf I into Kf into molarity. So this is equal to I, and in place of I we will write okay, del Tf is also given, which is 0.345. so we will put only the numerical value. In place of I we will write 1 plus 2 alpha. Kf value is given, which is 1.86, and molality, that is also given, which is 0.08. So from this equation we can find out what is the value of 1 plus 2 alpha, or you can also write it here I. So I will be equal to 2.32. that means 1 plus 2 alpha, that is equal to 2.32. so from this we can get the value of alpha, 1.32. so alpha will be 0.66. so we have to find out the percentage. Okay, so percent alpha will be 0.66 into 100, so this will be 66%. so this is also integer type of problem. So 66% of NHSO4, that is actually dissociating. That means in NHSO4 there is presence of HSO4, so it is producing only 66% H plus, that is hydronium ion, because H plus, when it will combine with H2O, it will be hydronium ion. Okay, now Van der theory of dilute solutions. We know that for ideal gas there is a equation PV equal to nRT, and PV equal to nRT, this equation how we get? By combining Boyle's law, Charles' law, Avogadro's law. Okay, now Van der, he found that there is some similarity between the behavior of gaseous molecules and the solute particles in dilute solution. So Van der realized that solute particles in dilute solutions, they possess kinetic energy just like gas molecules and move in random direction in the solution like gas molecules. Now there is, suppose, semi-permeable membrane, that is SPM, there is collision against SPM. So when there is collision against SPM, you can compare the situation just like the wall of the container in case of gas molecules. So there is also collision with the wall of the container. Now the collision against this membrane, the solute molecules, they will exert the osmotic pressure. So in case of gas molecules we simply say it is pressure, but now we are saying it is osmotic pressure. Okay, which is equal to the pressure which the solute molecules would exert if it were gas molecules at the same temperature and same volume as that of solution. Okay, so this osmotic pressure, we are saying that it is same as that of the pressure which the solute molecules would exert if it were gas, but it is not gas. But if it were gas molecules at same T and V, then they will be it will be the same pressure. Okay, so that means that the gas laws are equally applicable to dilute solution. So the gas laws, that is Boyle's law or Charles' law, we can find some analog equation for osmotic pressure also. So this is the Van der theory. He basically found this similarity between dilute solution and gaseous molecules. So that is why there will be some new laws, which is the combination of Van der law and the gas laws, that is Van der Boyle's law, Van der Charles law, Van der Avogadro's law, all this. Okay, so an analogy exists between gaseous and solute solutions provided osmotic pressure of solution is used in place of ordinary gas pressure. So for dilute solution, for non-electrolyte, these three laws are applicable. Okay, so Van der Boyle's law, That is a combination of Van der Waals and Boyle's law, then Van der Waals law and Van der Avogadro's law. So first we will see Van der Waals law. So in Van der Waals law, normal Boyle's law, what we know, that at constant temperature the pressure is directly proportional to the volume. Okay, but here we are saying it in a different way. At constant temperature the osmotic pressure of a solution is directly proportional to its molar concentration, okay, which is C. In Boyle's law, it is P is inversely proportional to 1 by V. That is, when the pressure is very high, volume will be low. Inverse relationship. Here also we are saying the law in terms of concentration, but actually what we know, concentration is basically number of moles by volume. Okay, so you can say that pi is proportional to C, or we can also say that pi is proportional to N by V. Now N is constant, so pi is basically proportional to 1 by V. N is number of moles of solute dissolved in V liter. So that is why N by V is basically the concentration C. Okay, so from this what we are getting, PV equal to constant, that we say for gas laws, but now it is pi V equal to constant. So it is analog of PV equal to constant. Okay, or you can say that pi by C is equal to constant, because with concentration pi is directly proportional, but when it is V, it is inversely proportional. That is why pi into V is constant. So this is Van der Waals law, that is a combination of Boyle's law and Van der Waals law. Next we have Van der Waals law. Now in Van der Waals law, for a solution at fixed concentration, that is concentration we have kept it fixed, the osmotic pressure, that is pi, is directly proportional to absolute temperature. So in case of normal gas laws, we say that P is directly proportional to T when volume is constant. Now we have kept the concentration constant, that means actually volume is constant, because concentration is related to volume. So here we can say that pi is proportional to T, or pi by T is equal to constant. So pi V is equal to constant and pi by T is equal to constant. That means what we can say, if we combine these two, we can write pi V by T, that is equal to constant. Okay, and we can also write it as pi V equal to, suppose the constant is K, into T. Okay, if it is 1 mole. So now we are getting pi, it is V, not V. Pi V is equal to KT. Now this equation containing K is the general solution constant. But Van der further proved that this K is actually equal to R. Okay, so we can write it as RT. So what we are getting, pi V equal to RT, which is just like PV equal to RT, and it is for 1 mole, but if there are n number of moles, it will be pi V equal to nRT. Okay, so this constant and universal gas constant that we use in gas law equations. But if these two are same, now these two are completely analog to each other. Okay, so pi V is equal to RT. This is for 1 mole, but if we say that there are n number of moles, now the equation will be pi V equal to nRT. Okay, we can also write it as N by V, and N by V is nothing but concentration. So two expression we can write here, pi is equal to CRT or pi V equal to nRT, depending on in the numerical what value is given, whether concentration is given or volume is given. So these two equations, that is equation A and B, these represent general solution equation. In case of gas, what we say, general gas equation. But now what we are saying, general solution equation, because now it is not gaseous system, it is dilute solution system. So that is why we are using general solution equation, this type of term. Okay, so in this way we can combine Van der law with Boyle's and Charles. And the third one is Van der Avogadro's law. So in Avogadro's law, first of all, what is the combined law that we will see here? Equal volume of dilute solutions. Suppose you have two solutions, both are having same volume but different solute. Temperature same, osmotic pressure same. T, pi, V all are same, only different solute. But what will be the result? They will contain equal number of molecules. So if V, T, pi, that is volume, temperature, pressure same, though they are a different solute, but they will contain same number of molecules. So this is the Van der Avogadro's law combined. But what is Avogadro's law? According to Avogadro's law, which is very similar to this law, but it is saying that at the same temperature and pressure, equal volume, that is V is also same, different gases contain same number of molecules. So you can find similarity. What is the difference only? Here it is dilute solution of different solutes and here it is different gases. That is the only difference. Otherwise these two are very similar to each other. So from Avogadro's hypothesis we can write that when temperature and pressure constant, then V is proportional to N, that is volume is proportional to number of moles. Okay. So whatever is the gas we have taken, suppose oxygen, nitrogen, hydrogen, whatever is the gas, it doesn't matter. If VTP, these three are same, then that is T and P same, then V is directly proportional to N. Okay. If you look at this picture, here T and P we have kept constant. All are having same volume, 1 liter, 1 liter, 1 liter. But different gases we have taken, hydrogen, nitrogen, oxygen, atom. Okay. So here number of moles of, that is N, that will be same when volume is same. That means if one is having volume V1, another having volume V2, then in the first case if it is N1 moles, in the second case if it is N2 moles, these two ratios will be same because V is directly proportional to N. Okay. So this is Avogadro's law, and if now we consider Van der Avogadro's law, this will be the equation, that is the final equation. Okay. Pi V equal to nRT we have already seen in the previous slide. That is from first law it is pi is inversely proportional to 1 by V, then pi is proportional to T. Remember in the previous slide what we, pi is proportional to 1 by V from Boyle's law, pi is directly proportional to T from Van der Charles law, and here it is number of moles which is directly which is proportional to the volume. Okay. So combining all these we are getting pi V equal to nRT. So for first solution we can write, suppose there are two solutions, number 1 solution, number 2 solution. So for the first one, pi 1 V1 is equal to nR, N1 RT1, R is same for both. And here for the second solution, pi 2 V2 equal to N2 RT2. But if pi 1 is equal to pi 2, V1 is equal to V2, T1 is equal to T2, so obviously N1 will also be equal to N2. Okay. So that is actually this Van der Avogadro's law, that equal volume of different solutes of equal volumes of dilute solution of different solutes, when temperature, osmotic pressure same, they will contain equal number of moles. That is N1 will be equal to N2. Okay. So this is a Van der Avogadro's law. Here we have a problem. A solution weighing A gram, that means the weight of solution is A, its molality is B. Molecular mass of the solute is unknown, that we have to find out. Okay. Molecular weight is unknown. Mass of the solute given, that is given mass of the amount of solute that we have taken, that is given, which is C. So we have to find out molecular weight. Now if you look at the options, all these options are in terms of A, B and C. So you have to express molecular weight in terms of A, B, C, and there is also 1000. Okay. So here mass of solution A, mass of solute C, right? And here mass of solvent will be A minus C. Okay. Now molality is B. Now according to the definition of molality, what we know that it is the number of moles of solute which is present in 1 kg of solvent. So we can write that 1000 gram solvent contains B moles. So in our case the mass of solvent is A minus C. So A minus C gram solvent will contain B divided by 1000 multiplied by A minus C. So this is the number of moles of solute, and we have to find out molecular weight of solute. Now what is the relationship between molecular weight and moles? It will be moles equal to given mass divided by molecular weight. Now in our case we know the moles, molecular weight is unknown. So now molecular weight will be given mass divided by moles. Now given mass of the solute is C gram. Okay, so we will write here C, and what we have calculated number of moles, it is this quantity, that is B into A minus C divided by 1000, but 1000 we will write here. So what expression we are getting? C 1000 divided by B into A minus C. It is matching with first option. Okay. So in this way we can find out what is the molecular mass of the solid. Suppose if the another way also the question may be given. Suppose the molecular mass is given in this, that is the answer that we have calculated here finally. If that amount is given and some other expression you have to find out, that may also be the possibility. Okay, but if you know what is the definition of molality, what is the relationship between moles and given mass molecular weight, this is not a very difficult problem. Okay, integer type of question. Freezing point of 0.2 molar KCl. Solution is minus 0.7 degrees centigrade. Now to this potassium cyanide we are adding HgCN2, another cyanide compound we are adding, where anion is same, cyano, but cation is different. So on adding 0.1 mole of this new cyano compound, mercury cyanide, to 1 liter of this 0.2 molar KCN solution, now the freezing point is increased, that is it is minus 0.7 degree, that is lower, very low value, but compared to minus 7 degree now it is towards 0, that is comparatively higher value. So what it means, we know that colligative, that is the depression of freezing point, that is directly proportional to the number of solute particles. Okay, so higher will be the number of solute particles, the del TF value that will be very high. So here if you consider del TF value, that is 0 minus 0.7, that means it is 0.7, but in case of this one it is 0 minus 0.5. So minus will be cancelled, it will be 5 degrees centigrade. So here del TF and this del TF, suppose this is prime, so del TF is greater than del TF prime. That means when there is no mercury cyanide, then the number of particles from the dissociation of KCl, and when HgCN whole 2 is present, now the number of particles obviously it will decrease. So that is why del TF is also decreased. Okay. And here what type of reaction is going on between HgCN2 and the cyanide ion which is coming from KCN, that is also given. So MgCN whole 2, it will react with m number of cyano ion and it will form this type of complex, HgCN m plus 2. So now the number of Cn is given in terms of m plus 2. So initially there is only 2 cyano with mercury, each mercury, but as we are adding m number of cyano, now it will be m plus 2 number of cyano. And look at the charge here. HgCN2 is neutral, but we are adding m number of Cn minus, so charge will be same as the number of cyano, that is the number of anions. So number of anions is m minus, so that is why the charge of this complex, that is also m minus. So we have to find out what is the value of m, and here it is given that you can consider molarity same as that of molarity. Actually for dilute solutions these two are same, okay, but if it is directly given it is fine, then we can easily solve the problem. So here first of all we will find out what is the value of I when there is no mercury compound present. Del TF I Kf into m. So I will be equal to del TF divided by Kf into m. Now del TF is this value, simply put 0.7, and Kf is, it is given or not? Sorry, we have to find out K, very sorry. I is known. I is known because after the dissociation of KCN, it will be 2 molecules, K plus and Cn minus. So I value is basically 2 here. So put I equal to 2 and m is equal to molality 0.2. So this will be 0.7 by 0.4, that means 7 by 4. You can keep it in this form or you can also calculate it. Now we will write this equation, that is HgCN2 reacting with m number of cyano and it is forming a new complex. Okay, so when we have added HgCN2, as it is combining with m number of Cn, so that is why now the number will reduce compared to the situation when there is only potassium cyanide. Okay, so initially the amount of HgCN2, it is 0.1, so we will write is 0.1, and MCN minus, the concentration will be same as that of the concentration of KCN, so we will write here 0.2 and this is 0. Now when this is T equal to 0 and when T is equilibrium, that is when equilibrium is reached, now HgCN2, that will be 0. So all of them will react with MCN. Now depending on the number of M, as we do not know, so 0.2, the remaining amount of cyano will be 0.2 minus M into 0.2. Minus 0.1 M, because with 0.1 HgCN2, 0.1 Cn minus will be added. Okay, so because that is clear from this formula, initially it is HgCN2, but now it is given in the question, it is m plus 2, that means m number of cyano will attach with this 0.1. So it will be now the remaining concentration of cyano will be 0.2 minus 0.1 m, and this complex that is produced, this will also be 0.1, because from 1 mole of HgCN2 you are getting 1 mole of this new complex. Okay, now we will find out what will be the total number of moles at equilibrium. Okay, so total moles at equilibrium will be moles of that is K plus, moles of Cn minus remaining. There is no AgCN2 because all of that is all the amount of AgCN2 that is consumed, and the concentration of this newly formed complex, that is AgCN M minus. So the number of K plus, that is the moles, it is 0.2. For Cn it is this value 0.2 minus 0.1 m, and for this one it is 0.1. So after calculation it will be 0.5 minus 0.1 m. Okay, so we have to find out what is the value of m. Okay, now when this reaction is taking place, the corresponding del TF is 0.53. So now using the same equation, but now we will write 0.53 equal to Kf. Kf value is known, I okay, so this is 0.53. In place of I we will write 0.1 m. So here basically one mistake I have done, that is we will not consider I. Why we will not consider I? Because in M directly, as we have already calculated, this is the total number of moles and volume given is 1 liter. So in 1 liter basically this number of moles present, and that is also, that means according to the definition this is molarity, because this number of moles is present in 1 liter. So if this is molarity, this is also molality, because in the question it is already mentioned we can assume molality and molarity both are same. And as in this molality we have already calculated that what is the amount of Cn minus left. So separately we don't have to put the value of I, because when we have calculated molality, then we have already considered what will be the total number of particles. Okay, so that is why I value we don't have to put here. So this is molality, and Kf value we have calculated at initially, which is 7/4. So in place of Kf we will write 7/4. This is Kf value and this is M value, that is molality. Don't confuse between these two M. This is actually molality. Okay, because we also express molality, and here we have another small m which is given in the question. So here this m value we have to find out, and from this equation, that is 0.53 in equal to 7/4 into 0.5 minus 0.1 m. From this equation we can find that m will be equal to 2. So this is an integer type of problem, and the value of m, that is 2. Okay, I hope it is clear that why we have not considered I here, because while we have calculated molality we have already considered what is the number of moles, and as total number of moles that is present in volume 1 liter, that means this is also the concentration molarity. That means it is also equal to molality, because here this condition is given. Okay, so directly we are putting the we are using this equation del TF equal to Kf and M. We are not using I here. Okay. Next problem. A solution is prepared by dissolving 1.08 gram human serum albumin. Now this is a protein which is found in blood plasma. Okay, and the volume of this aqueous solution that is given 50 centimeter cube, 50 cc. Osmotic pressure is given 5.85 millimeter, that is pi value is given, and temperature 298. So two questions we have here. What is the total, what is the molar mass of albumin, that is molecular weight we have to find out, and the height of water column placed in solution. Now this is a completely new thing. So in this question, if you know what is the relationship between the height of water of column and the osmotic pressure, this type of problem you can also use the same formula. Suppose if water height related problems are given, so if you understood this particular problem, you can also solve the other problems. So here we have a picture. So what this picture actually signify, this is the solvent, okay, and in this the shape that is given here, it is containing solution. That means inside this funnel there is solution, outside is solvent, and there is SPM, semi-permeable membrane. So that means according to osmosis, we know that from low concentration the solvent molecules, it will move towards high concentration. So as it is moving from this solvent towards solution side, the height of the that is the height of the solution which is present inside the funnel, that will be suppose at this particular height, and this height is actually denoted by H. So if this is the case, then osmotic pressure pi is equal to H rho G. So what is rho? Rho is the density of the solvent, and H is height, and G is, this is acceleration due to gravity, because when this is moving upward, it has to face the acceleration due to gravity that it has to overcome. So that is why osmotic pressure is also equal to H rho G. So here we have to use this equation, okay. So that's why you have to understand this picture first, otherwise why this type of relationship is there, that we will not be able to understand. So pi is equal to CRT, that you already know, but it is also equal to H rho G. So if there is problem where you have to find out the height of water or height of solvent, then you have to use this equation, okay. Now for the first one, that is question number A, we will use the equation pi V equal to W by M, that is number of moles, nRT. We can also write it as W by M RT, okay. So it will be M equal to W RT by pi V, okay. Now W is given, that is the weight of this serum albumin 1.08, R is 0.082, temperature given 298. Now be very careful about the units, as I always say that pi is given in millimeter He, but you have used universal gas constant which is in liter atmosphere, so you have to convert it to atmosphere. And how you can do so? 5.85 divided by 760, okay. So we will put this value. So we are converting millimeter to atmosphere, so now it is in atmosphere. 5.85, in place of pi we will write this value 760, and volume is 50 centimeter cube, but you have to convert this centimeter cube to decimeter cube, because it is in liter atmosphere and dm cube is actually liter. So when you are converting 50 to, that is centimeter cube to decimeter cube, this will be equal to multiplied by 10 to the power minus 3, that means 0.05. So here in place of volume we will put 0.05. Now it is in liter and this is in atmosphere. So from this calculation you will get the value of molecular weight, which is 68571.2 gram. So this is the first question's answer. Okay. Now for the second part we have to use pi equal to H rho G. But before that we have to know what is the value of g, acceleration due to gravity. It may be given, it may not be given, so better you remember the value. 9.8 meter per second square. See the unit, it is in SI unit. So we have to convert all the other terms in SI unit. 1 atm is equal to, now atm is to be converted to Pascal. 101325 Pascal is written as PA. So if this is equal to Pascal, that means what we will do, this 5.85, this is the pressure, right? So with it we will multiply 5.85 divided by 760 multiplied by 101325. Okay, so now this is the pressure, that is pi, and here density is given, that is for water it is 1 gram per centimeter cube, but this is not in SI unit, so we have to convert gram to kilogram and centimeter cube to meter cube. So when we are saying that D is equal to 1 gram per centimeter cube, now in place of gram just put the kg, so obviously it will be 10 to the power minus 3 kg, and in place of centimeter you will put 10 to the power minus 6 meter cube, because when you are shifting from centimeter to meter it is 10 to the power minus 2, but as there is cube, 10 to the power minus 2 whole cube, it will be 10 to the power minus 6. So ultimately density we are getting 10 to the power 3 kg meter cube. Now use the equation pi equal to h rho g. So pi is 5.85 divided by 760 multiplied by 101325. So this is the value of pi. H is unknown, that we have to find out. In place of rho we will write, this is the density, and g is 9.8. So if you do the calculation you will find the value of h in meter, obviously 0.0796. okay, now depending on if you read the question carefully, whether it is asking the answer in particular unit, if it is mentioned, accordingly you have to do the problem, but here it is in meter. So if it is asking in centimeter, you can change the value to centimeter also, and it will be 7.96 centimeter. So this is the height of water column placed in solution. Okay. The partial pressure of carbon dioxide in air which is saturated with water vapor. Temperature is 25 degrees centigrade, pressure 1 atmosphere pressure, and this is the partial pressure. Okay. Now Henry's constant for carbon dioxide in water, that is given. Now be very careful about the unit of Henry's constant. Look at the unit, moles per liter per atmosphere, that means it is concentration divided by pressure unit, right? And for carbonic acid pK value given 6.37, you have to find out the pH of normal rainwater, that is CO2 mixed. So pH of normal rainwater, it is nothing but the pH of H2CO3, that is carbonic acid. So this problem is actually combination of two chapters, that is solution and also the ionic equilibrium. But here first we will see that how to which equation we will use. Okay, so there are actually two equations. Sometimes we say that Henry's law constant solubility is equal to Kh into P, and sometimes it is written as partial pressure that is equal to Kh into concentration or solubility, because solubility is nothing but also concentration, but it is a maximum concentration that is possible. So when this expression is used, basically it is the unit of Kh should be S by P unit, that is in our case concentration by pressure. But if the second equation you consider, then P by S will be the unit of kH. Okay. Now, though we write kH, but actually the thing is different. There are two ways by which you can express this equation. If the constant, that is kH or any other constant, it is defined in terms of solubility by pressure unit, that is concentration by pressure, it will be referred to as Henry's law constant and Henry's law solubility constant. So this is actually denoted by capital H, but you may not find it in some books on numericals. Suppose it is given kH. Though here the constant is not mentioned, only the value is mentioned. It is not mentioned whether it is capital H or kH. Okay, but it should be actually H. And if the proportionality constant, this is also proportionality constant, that is the relationship between S and P is proportional, but proportionality constant you can put either pressure side or in the solubility side. So when the proportionality constant is pressure by solubility, that is the second case, then it will be called, the corresponding constant should be called Henry's law of volatility constant, and now it is kH. But here I have written both kH, but actually it should be written as H into P. But it doesn't matter, just read the question carefully, look at the unit. So if the unit is concentration by pressure unit, that is solubility by pressure unit, then you have to use the first equation, otherwise use the second equation. So here obviously we will use the first equation. We will find out, as kH value is given and partial pressure is given, so we can easily find out what is the value of S. So S will be 3.04. This is the partial pressure which is given. Partial pressure of CO2 in air saturated with water vapor at 25 degrees centigrade and 1 atmosphere. It is this value, 10 to the power minus 4 atmosphere, multiplied by the constant value, that is 2.3 into 10 to the power minus 2. Regarding unit, there is no problem because it is atmosphere, this is also atmosphere. So the solubility that you will get, it will be 6.99 10 to the power minus 6 moles per liter. So this is one part we have completed. We have already found what is the value of S. Okay. Now H2CO3, that is the acid for which we have to find out. It is nothing but rainwater. Okay. And we have to find out the pH. So first of all we should know how it will be dissociating. So it will be dissociating HCO3 minus and H plus. Now here pKa value is given, but you can think that there should be two pKa values, but as only one pKa value is given, by default you can consider it is the first dissociation. Okay, so if initial solubility is S and 0,0, then at equilibrium it will be S minus S alpha, where S alpha is the degree of dissociation. This is also S alpha, this is also S alpha. Now the value of Ka, that will be equal to concentration of bicarbonate, that is S alpha, into concentration of H plus, that is S alpha, divided by S common 1 minus alpha, this value. So SS will be cancelled, and here alpha value, as it is very small, so 1 minus alpha, it is almost equal to 1. So to simplify the equation, now we will write S alpha square divided by 1. So from this equation, the value of alpha will be root over Ka by S. Okay. Now if it is root over Ka by S and we need the value of pH, that means we should know what is the value of H plus. Now for H plus, here we have considered S alpha, so this is equal to S alpha. Now in place of alpha we will write root over Ka by S, that is this value. So this will be equal to root over Ka into S. That means if now we take log both sides, suppose now we are taking log H plus, so in the right hand side what you will get, half log Ka plus log S, sorry it is capital S. Okay, now we know that negative logarithm of H plus is pH, so we will put negative sign here, so there will be also negative. Okay, now I am moving here. So pH will be equal to, if you insert this negative sign inside the bracket, it will be half negative log Ka, which is nothing but pKa, and minus log S. And what is the value of S? We have calculated in the first part, 6.99 10 to the power minus 6. Okay, so put the values of pKa. It is 6.37, which is given in the question, and log 6.99, that means it is actually log 7 minus 6, because log 10 to the power minus 6 is minus 6. So ultimately it will be basically log 6.99 minus 6. And after the full calculation, the value that we will get is 5.76. So here options are given. This is the correct option, 5.76. Okay, I hope the problem is clear.